So you've learned about the stack, and I'm sure you can write a simple function. So we're going to do, in C, do this all in C with no assembly. Okay, and that's the target, because we're going to have to fool the compiler a lot of times. So we're going to have a main function. We will have a test underscore entry function, and we'll have an int x is equal to test entry, and then test underscore exit will pass an x, return 0, essentially. And I'll program on a computer so you can see it. So this test entry will simply print entry. The exit will print exit along with this number that's returned. Doesn't matter what the number is. So this is what we're first going to set up. Now what we're going to do, though, is at runtime, when we return from test entry, we're going to call another function. And that function is going to print, inside this function. Okay, but here's the thing: we're not going to use, we're not going to encode like a function pointer directly into the code to call it. What we're going to do is we're going to replace the return value on the stack, so when this guy returns, he returns this function. Now there's a couple tricks you have to do. It's very easy to do those tricks if we did assembly, or we just hand coded some bytecode here and called it, right? But we're going to use the compiler to do it, which means you have to understand the calling convention in order to do it effectively. Because when we want to return back to this main program and exit normally, which means when we return here, we got to be correct in the stack. If we just put on the stack to return this guy's nowhere to return. Even if we fix up the guy to return, you're still off one stack location. How do you get that stack location back? So that's what we're going to try to do, using just C. Okay? And anytime you think you can try to do it yourself, just pause the video and start working on it. See if you can get it done. You don't have to watch this whole video and wait for me to do it. I'll try to help you along, and I'll do it as I go. Figure out what to do. But if you ever feel like you want to try something, because there's a number of ways you could try to do this. And we're going to be doing 64-bit. So you should make sure you're compiling at 64-bit so that you can get this to work. And the first thing we're going to have to do is I'm not going to turn off optimizations. I'm going to try and get these functions not to be optimized out to the code, which is going to happen if I just code like this. So we're going to try a couple things to try and avoid the compilers. There's a lot of things you can do. I'm going to do a simple, very big hammer on it, though, to begin with. So, if we got any errors in there. Simple enough program. The crash works. Now we want to see, though, so as you can see, our functions don't exist in here, right? It just directly calls printf, and it directly just puts deadbeef as a second parameter to printf. So our functions are gone, right? So if I try to do, x stack program test underscore asterisk, they're not here. Okay, so let's see if we can stack program .def. Let's do this notepad thing. Exports. And we're going to force them to be there because they're exported. So since they're exported, they're going to be forced to be in here. All right. Yeah, I think I'm just going to have to, since I don't remember, linker flags. We'll just add it manually. Linker flags /def stack program.def. Okay. let's do this, CDB. And now we're going to see if those functions have not been removed. So this is stack program, test underscore asterisk, and there they are. Let's see what the exit function does. It puts EX and ECX and EDX, blah, 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 does a string, jumps, blah, 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 who cares. And let's see what the entry function does. Yeah, we really don't care too much what it does, but yeah, it's going to return dead beef. Okay, it's fine. It's going to do that. But the main question we have is the main program is not using them, which is what I figured. So the main program still is optimizing them out. So what does that mean? Well, it means we're essentially going to have to do some type def uint pfm entry void type def void pfn exit uint value. So what we're going to do is we're going to create function pointers. And the only reason we're doing this is so the compiler doesn't compile them out. You can try other ways if you want. pfn entry. I'm only going to check error codes. So pfn entry is equal to get proc. I thought I might have gotten them reversed. Okay. And let's take a look here. So we're calling get proc address. We're calling them. Okay. And if I just run it, we got what we want. Okay. So now what we're going to do is we want to call this new function here. We'll do a void function, test. How about the inception? And this guy is just going to print inception. So now how are we going to do this? We don't want to create a function pointer, just call him, right? Intercept the return, right? So we are going to have to put this guy in the middle here, and we're going to have to do it within this function here. So if you remember, we'll come down here. So remember how we talked about before. So no matter what, for 64-bit, we never clean up the full stack until we completely exit the function. That's the first thing. Second thing is that the stack will always look like this for every function. It'll have 4 places. It'll have the return. All right, so we're back. Sorry, someone came to the door. So here you have the return address, and then you're going to have at least one location for alignment. Because, as we said before, in the 64-bit calling convention, you must be aligned to a 16-byte address. So that means that if we simply did the following, right? So let's say that we just replaced the current return address with test intercept. In fact, let's copy this over. So we would just replace that address with test intercept. So when test intercept runs, test intercept at his entry point will be at this stack level. And since test intercept calls printf, he's going to create, there's no return address on the stack now, first of all, so we're just going to crash because we had to set that up. But ignoring that, if we just did this, test intercept is going to create this as the align, which is going to be incorrect because the alignment's here, not here, right? Every other one's in alignment, so it was already at an alignment, but it's not expecting that because because you're within the function, you're at an alignment. So you make a call, you can become unaligned, and so you have to realign it. And so it's expecting that a call has been made into it, right? So let's do that first, though. So how we're going to do this here is we will just say ulong, this is intercept. Now, the problem we have with this function is we have this first variable here. However, we have no idea where it's going to be on the stack down here, right? So that's our first problem. So that means we need to actually create an input value. So instead, we're going to pass in an input value now. And again, for us, it doesn't really matter. We don't care what the input value is here. But in order for us to get the address, we need a place we can securely know that every time we get that location, it will be at that address. So now that we've created int value, we now need to create, instead of this intercept, a pointer to this intercept. And we'll call this intercept address. Let's go to this intercept address. So now this intercept address is going to be equal to, if we took value, so when we take the address of value, we will get this address here. Oh, sorry, over here. We will get this address here. So we get the address of this function, or this first parameter location on the stack. Right below it's a return address. But what I'm going to do is typecast it to an unsigned char. That way, when I add or subtract this value, it's done in bytes, because the compiler will do this at size of operation. So it would do it in bytes here. I could also change this to ulong and subtract 1. And that would actually be the same thing. It should now subtract 1 since the stack is in 64 bits. So I could either do unsigned char and subtract 8 bytes, or typecast use a compiler to go down. So we're going to try to use the compiler to go down. Now once I get to the return address, we are going to put in test intercept. Now we actually should just return to test intercept, but we're going to crash. And let's see how we crash though. The question here is, so if you remember, we're going to create this new alignment here, and we're going to call printf. So, or we're going to jump to printf, because we're just doing this. So let's change this then to go back to uint, to force it so it doesn't just jump to it, because we need to be, because I want to see when we crash coming back up, or if we crash going into printf. So a bit easier. So we'll just return 1. Okay. Come up here, put this here, and we're going to return 1. So to go over what we've done so far, we have called test entry from the main, and then within test entry, we are at this location. We are now replacing the return address with test intercept, and we should go here. Now the question is, we're going to crash. There's two places we can crash. We can crash inside printf if someone tries to do an aligned move, because the stack is going to be unaligned. Or we're just going to crash coming back because we haven't set up a return path. Right? So let's see if this compiles. Does not. Oh. That's why. I forgot I was dereferencing it. Okay. Let's set our breakpoint here, and let's go forward a little bit here. Now we're going to call test entry function, right? We're going to subtract some. We're going to get our string to print, and we're going to print it. Now we're going to get our dead beef, and we're going to exit here. So it actually did not do our code. It completely ignored it. This code here was completely ignored. So let's do this. It may just, again, optimize it, you know. Sometimes you have to call something else just to get this stuff to stick, because it optimizes everything out all the time. You know, that's why I'm, for these types of things, you have to sit there and debug it and make sure. Actually, static program, test entry, unassemble that thing. Oh, test entry function. Okay, so yeah, we're just going to put that in R8. Oh, we are going to put it in there then. Okay, so now we're actually going to do it. Okay. Why did I get out of it? Okay, BP, oops, crap, BP stack program, test entry function. Okay, now we're at test entry function. Okay, so before we do this, let's just do a K. Right, so far, so good. That's right. We're at the right location here. Okay. Oh, so we didn't, never mind. We didn't subtract Rx 8. Okay. Go over that once. Okay. So let's go printf, right? Okay. We're returning to the right place. We're returning test interception. So we had to replace the return on the stack to instead go to test intercept. So you see up here, let's see what that is, 978. Back up here, before we replaced it, keep going up, 978 was returning to the middle of main again, right? Okay, so now let's look at the stack pointer. RSP at this point is not aligned. We return here. RSP is aligned. You know it's aligned because this last nibble has to be 0. Now we're going to unalign it though. As I mentioned before, now it's unaligned. So now we're going to call printf. So we'll crash in printf. Does not. But now it's going to crash here, because where are we going to go to? We're going to go to 5. So we're going to crash at 5. Okay, so we still run the risk of having this unaligned issue. So we need to, and it doesn't really matter, but we need to keep 4 stack locations when we return back to main. So we'll call test entry. We replaced the return address. So instead of returning here, we've now returned to test interception. Then we're going to return back, but we need to return back with this. So what does that mean? How do we align the stack again to where we would have this? So remember, whenever we make a call, we're here. And then that function is going to try to align something. And if we try to return again, we're going to use that value. Now, if we return to another function at this point, and that function calls another function, this could be one way. So what happens then? Well, if it calls another function, we will have another 4 locations on the stack. Then we will have a new return address. And we'll have an align. Okay? So, if we could, for example, replace this return with a shell return. And these returns don't do anything. These functions do nothing but return. 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 Now this here, this one has to return to the original. So what does that mean? Well, that means this intercept function needs to take a parameter now. The return location. The original return location. Otherwise we lose it. So now we have that. But how do we get it? How do we get back? How do we get that original return location? Well, what if we put it here and then just moved it down later? We have it here, move it down. Okay, so now that we're in here, let's call another function within here. But again, we need to be able to have all of these functions inception times 2. We need access to the parameters, of course. And we will now move our printf to the second inception. And again, down here, we don't care. We'll worry about the return value later. Actually, maybe even make that something you guys can figure out. So we're going to call this inception 2. So now you will be in inception 2. And in fact, maybe we'll print both, right? Print inception, and we'll print inception 2. Oh, actually, at this point, we're not aligned. Oops, where's our thing? So what we have to do is do a double return. If we do a double return, that was the other way, is doing the double returns. So, because we're still unaligned here, which would mean we would still need at least one more return to go down, right? So then we could align the stack properly. But now, I'm thinking, what if we... The problem with this is we don't have a place to put the return original. So if we came all the way up to this return, for example, so if we just return, let's see here. So that's aligned, that's not aligned. That's aligned, that's not aligned. That's aligned, that's not aligned. That might work then. Since this one's not aligned, we could put the return to the original here. We could put our test inception here. So let's see how this plays out then. As our second option. This is the one I'm thinking might be more promising. So what we're going to do is we're going to return to our return shim, and then here we will have inception. Oh, we have, okay, we'll do 3 return shims. Return shim. So each time we're just going to pop up the stack. And we get to inception, we pop up the stack again. We're original now. And how should this work? So let's see where the alignment is. So this is not, this is aligned, this is not, this is aligned, this is not. Okay? So now we'll be here. And then if we make another function call, we'll have 4 of these on the stack. At least. And, oops. So you have 1, 2, 3, 4. Oops, sorry. So we're going to have some unknown here. unknown. And then we're going to be, sorry, that will be not align, not align with our 4 parameters here, 1, 2, 3, 4. And then we will do the new function call. Right? And then we'll be aligned here. So as you can see, what we're going to do is return test and here. We're going to return. Store the original there. Test inception. Now we're going to come into this function with this as our return address, which means this function should have some parameters so we can grab that original return address and pass it to the next function. And then we'll be like this. Now what we want to do is return to the original location. So we want to end up putting original location here. And 2 return gems. So that is the craziness we're going to try to do. So as we saw this before, we have our test entry that we're going to call with 5. Doesn't matter. Then we are now putting this interception in. However, so we're now putting this interception in. However, we instead, we will do, so let's do this. We will say iterate parameters, original return address, right? So we will do that. For iterating parameters, we just need that. So now what we're going to do, we're going to save the original return address. Right? So now we've saved the original return address. Now the next thing we're going to do is overwrite the return address not with test inception this time though. We're going to do it with test shim. Now what is test shim? Test shim is just void. We will try and export it just so that it does not go away. Does nothing. Right, so we have essentially what we're going to have now is we had this setup, and now we have return shim, and we have the original value. So now we want to put return shim, test intercept, original value, right? So iterate parameters. Okay, well, parameter 0 is also test shim. Parameter 1 is test shim. Parameter 2 is our intercept. And parameter 3 is our original address. We don't need this for that one. So now we have populated the stack like this. Hopefully. We'll test it out and see if it works. But we should be returning to the shim, return to the shim, return to the shim, return to the test intercept, and we'll have the original org there. And so that's as far as we're going to test right now. The shim won't do anything, and we won't print anything, won't do nothing because we could be at unaligned locations. And then within intercept times 2, we will be right here. And we will have to, again, populate to, because once we are at here, right, we'll have return address, right? Then we'll have some unknown stuff. Then we'll have 1, 2, 3, 4 parameters, the return, and the align. We need to do 2 return shims and put it back in the original return. Now this doesn't pass through EAX, the return value. So we're going to miss dead beef. But we will be able to hopefully cause this to be shimmed. So, however, we don't want to do this now. Oops. That's right, this is already right. So we're going to pass in the return location. But we either need to pass in the value of the return location or the location. Doesn't matter. Since we've got a p-void, we can always pass in the address. Okay. And so let's see how this works before we do anything else. It's probably not going to compile, but 99 test exception x2 not find. We need to do this, and we'll have to see if we need to export anything to prevent it being compiled out. Okay, so where we want to be, ng function, right? So right now we have this, right? Now, it actually optimized all that stuff out, except for our first one. So what we're going to have to do is come back in here. First thing we're doing is we're going to, so we don't have to mess around. We're going to go into our def file, just export all this stuff so we don't have to worry about them not existing, still exist. Again, this is not a real program. We're just messing around. The second thing we need to do is what we did here already. Let's print all this stuff. Just by passing these in, they can't change those values. Because unless they really understand what printf is doing with them, they really can't say, okay, let me change them. Because printf could be modifying them. They don't know. So set a breakpoint there, come in here. So now we're going to see that they're probably going to be populating everything. Let's see, inception, printf. Okay, now we're at the ret. So now we can come up here and see what we have. We're returning test shim. Return this test shim again. And then we're returning the exit function. But look at that. So we messed up. Did I mess up? Huh, I got those right. So those got messed up somehow because at this, we're returning to stack shim, we're returning to test shim again. What we should have had is a test shim here, a test shim here, a test function exit, and then a return. And I know what the problem is. We only have, well, shouldn't matter. This thing's not supposed to be interpreting that. It's supposed to just let me do this. Yeah, primitive 0, 1, 2, 3. Okay. We do this. Make them plain up. Make them volatile. I mean, at this point, we're just trying to mess with the compiler. So these are all things you run into when you're trying to outsmart the compiler. Entry function. Just look at it. We have test exception 2. We have shim. Okay. Let's go to the end here. All right. It's better this time. Because we have the return address. We have 2 shims here. Ah, it optimized. Or did I put them out of order? No, I didn't put them out of order. It optimized, thinking that this should be, so it messed up because it's not supposed to, I mean, this here, and this, I mean, I'm getting it here before I do this. But what it's doing is putting test shim in here when I haven't even done test shim yet. Original address should not have test shim in it. What happens if I do this then? See, you run all kind of weird stuff sometimes. Okay. Get through this. What does it look like now? Now it's perfect. So now we're going to return to stack test shim. That should do nothing. Should do nothing. This one here. Oops. We're going to come back down and call our other function. At least we should, but we're not going to this time apparently. We're going to just do that string. Oh yeah, but I put x2 on there. That's probably the reason. Never mind. Or is it auto? No, I didn't put x2. It's optimizing out test exception. That's a problem, because we need those extra 4 things up here. We do some stuff here that's never done. This is never done. Because when we come down to intercept 2, we won't do this. And so that way, if these 2 are exported, you can't optimize them out. Because you can't come in here and print this out if I called this function. So that should be the case. All right. Okay. Okay. Just gonna move fly through this thing. Okay. So now we have test interception. Let's see what that does. Oh, it's inlined in here. In this here, we're pretty close because whenever we have, as I've seen before, we've exported the inception and exception x2, and inception calls exception x2. The problem is that in the code it calls it, but in the actual application when it's compiled, if we take a look at stack program test, and inception, it doesn't call exception x2, and x2 does exist separately because they're exported, so it has to exist. So how we got around the last one? Well, we called get proc address. Now the problem is we can't call it. Why we can't call it this time? So the reason we can't call it this time is simply because we don't have 4 stack locations. Well, no, we have 4 stack locations. Oh no, we're aligned? Yeah, I think we're aligned. So actually we might be able to call it then. Might be safe. As long as we were aligned, we had 4, yeah. So actually, never mind. I think we can call it. We can do our little trick again. Because there's other tricks I was thinking of trying. For example, since we know we're not going to go down the stack, we're going up the stack, we could actually try and store it down somewhere else in the stack. Of course, it is a little iffy, because we're still running in the function whenever it happens, so we don't want something to override it. So, but I think that if we did our little trick again with get proc address, and exception 2, it takes a return location and it returns something. So just do the old type def again, pmn. All right, so as I said before, we had to do this little trick again, just so the compiler will remove this function call. That's all this is for. Gets the function address and we call it now. So, as we said, we're passing in to exception 2 that return address. Now, you remember what I said before, we're just going to change these all to these inceptions. We'll change them to void. Yeah. 2 to void. It's not going to work, but we're just going to do that for right now. So, void. All right, take out these returns. So that should never be printed. Yeah. I would say you should not see this. So let's say that. Okay. So what we've done here is we passed the location of the location. So we're gonna we'll just copy what we have up here. Just copy this. Done here. So again, we're probably going to have to do that stuff in here again. But so essentially what we're going to do is we're going to say, iterate parameters. And iterate parameters is going to be the, this is actually let's call this p original address. Right. So the original address was our location. Original address location. Right. And then we'll save it to original return address. Okay. So that's the first thing. We've saved the original return address. Now, oops, sorry, we actually had to subtract by 1, I forgot. Nice one. Okay, so now we got the original return address, and in order to get back down to where we're supposed to be, which is here, got 1, 2, 3, 4. So 0, 1, 2, 3, 4. So now put the wrong place. I shouldn't have done that. I know what I'm doing. Okay. So original location is that minus 4. That should be right. And then we get that address in. Okay. So now what we need to do though is iterate. So for now the inception address oops, a mistake here. It's actually not ampersand. So stupid. It's supposed to be here. And then semicolon. So B, this is shim list. Okay. Take that address, because that here is we take the original location because we passed it in as a ampersand. So now that we have the original location, we subtract 1, we get that location, we populate it. So if you remember, with the text intercept, we were here. And so now we were at this first parameter here. We returned it, we got the original address. And then we want to put it 1, 2, 3, 4 down from that. So that's what we just did. So now the next thing we want to do is get this shim list, take this return address that is on our stack way down here somewhere, and we want to this is less than that. and this shim list plus plus. And what we do here, that is going to be equal to this shim. We don't need the rest of this stuff. This will be interesting to see if the compiler I don't even care about what these do. I'm just trying to 2, 3, 4. Okay. All right. Okay, it's not gonna compile. Oh, it did compile. Okay. It's not gonna work. First time, never does.